In the last posting, we looked at the derivation of the dependence of the Nusselt number on Reynolds number and Prandtl number for laminar flow over a flat plate, parallel to a flat plate. And now we're going to go ahead and extend this to looking at the heat transfer coefficient. So this is something that's a little bit easier to tie to directly experimentally observable quantity. So if we had a flat plate, let's say it was at a uniform temperature and there was flow over that plate with a free stream velocity of u infinity, and let's say the free stream temperature was T infinity and the plate was uniformly at a temperature of Ts, then we could imagine that we might be able to locally measure what the heat flux was leaving that plate into the flow. And if we divided that heat flux by the difference in temperature between the plate and the flow, we would arrive at the heat transfer coefficient from the definition of Newton's law of cooling. And if we were to do that and measure the heat transfer coefficient at different distances along this plate, where x here is defined as the distance from the leading edge, then we'd find that for a certain free stream velocity, we would see a heat transfer coefficient that decreased rapidly as we moved away from the leading edge. And physically, we could assign that decrease to an increase in the thickness of the boundary layer. So we know our boundary layer is defining the hydrodynamic boundary layer, or velocity boundary layer is defining the thickness of the region affected by the surface, which we're defining as the region where the velocity is slower than 99% or 0.99 times the free stream velocity. Now, likewise, we have a thermal boundary layer, which we know doesn't have to be the same thickness as the velocity boundary layer. And before we said that the thickness of those two layers was related between the ability of, by the ratio of the ability of momentum to diffuse to thermal energy to diffuse, and that was given by the Prandtl number. And so the Prandtl number to the 1/3 power largely gave us the ratio of the thicknesses of velocity to the thermal boundary layer. But we know they're proportional to each other, and as the velocity boundary layer thickens, so does the thermal boundary layer. So this thicker boundary layer, as we move further from the leading edge, results in a lower temperature gradient. It's resulting in a lower velocity gradient, which corresponds to smaller shear stress at the surface farther away from the leading edge. Basically, at the leading edge, the surface is able to quickly remove lots of momentum from the flow. Back here, further away from the leading edge, the surface has to allow that momentum to diffuse through a much thicker boundary layer before it can remove it from the flow. And the same thing is happening for thermal energy. As the thermal boundary layer thickens, the temperature gradient in the boundary layer is decreasing. That's decreasing the rate at which heat is conducting at the no-slip layer right adjacent to the surface, and that's decreasing the heat flux. So as we move further along the plate in X, the heat transfer coefficient, the heat flux for a given temperature difference between the free stream and the surface, is decreasing. So as the boundary layer thickens, the temperature gradient decreases and the heat flux decreases. And we can express this mathematically from what we've already looked at, the dependence of the Nusselt number on Reynolds number. We know that the Nusselt number is increasing in the laminar regime at the rate of Reynolds number to the 1/2 square root of Reynolds number. We know the Reynolds number depends linearly on x, free stream velocity times x divided by nu. So the Nusselt number is increasing as x to the 1/2. But the heat transfer coefficient depends on the Nusselt number times the thermal conductivity of the fluid divided by the length scale. So in this case, H is going to be decreasing for this specific case as x to the 1/2 power. So it's, or x to the minus 1/2 power, 1 over x to the 1/2. So as we move along away from the leading edge, we would expect the heat transfer coefficient to decrease rapidly. Now, of course, the Nusselt number being dependent on the Reynolds number to the 1/2 also depends on the free stream velocity. So we would expect as the free stream velocity increases, as there's a faster flow, it's more capable of removing thermal energy from the surface. We're bringing colder fluid closer to the surface at a faster rate, and we're also decreasing the thickness of the boundary layer. And that increased flow, which tends to sweep away, bring in fresh momentum and sweep away thermal energy, is decreasing the boundary layer thickness compared to a slower flow, and that results in a higher Nusselt number. And namely, the Nusselt number should increase as velocity to the 1/2. And indeed, if we change the free stream velocity from 10 to 20, so we double the free stream velocity, we get an increase of about 1.4 times, or square root of 2. And if we graph the Nusselt number versus position along the plate for a single velocity, this is for 10 meters per second, then we see that increase with distance obeying a square root dependence, because the Nusselt number depends on the Reynolds number to the square root, and for a constant velocity, the Reynolds number is increasing linearly with distance. But if here we've only treated a distance up to 0.7 meters for this plate experiencing flow at 10 meters per second in air. And if we go to a significantly longer distance along the plate, we see a more complex behavior. Now for two different velocities at 10 meters per second, again, we see a rapid decrease in the heat transfer coefficient with distance from the leading edge up to about 3/4 of a meter. And then we see this rapid increase. And following this rapid increase, there is a rather slight decrease in heat transfer coefficient as we go to greater and greater lengths. And what we're going to talk about in the rest of this posting is the reason for this increase. And that increase is the result of the transition to turbulence in the flow. So we move from a laminar boundary layer where the flow is very smooth to a turbulent boundary layer that is stirring the flow and providing a great deal of mixing, and that is dramatically enhancing the heat transfer coefficient. And we know that the transition between laminar and turbulent for a flat plate, as we discussed in class, was equal to, or occurred around, a Reynolds number of 5e to the 5th. So when the Reynolds number exceeds 5e to the 5th, we transition from a laminar flow to a turbulent flow. In reality, this transition happens over some region. It's probably not as abrupt as we would tend to show here. And as we go to higher Reynolds number, the flow is turbulent and provides superior mixing. So the Reynolds number depends on the free stream velocity, in this case 10 meters per second for this curve, and the length scale, which is the distance from the leading edge. So for a given velocity, we expect a transition at some distance defined by that critical Reynolds number and the viscosity of the fluid. For a higher velocity, we see a similar behavior, but we see this transition much sooner. And that's resulting from the fact that Reynolds number, again, the critical Reynolds number where transition occurs between laminar and turbulent flow, is 5e to the 5th. And that Reynolds number is equal to the free stream velocity times the length scale, x, divided by nu, the kinematic viscosity. So as the free stream velocity increases, the length required for transition decreases. But in both cases, we see this decreasing trend for heat transfer in the laminar regime as the boundary layer grows, and then a rapid increase in heat transfer as we switch to a turbulent flow where there's better mixing. Now there's still a decrease in the heat transfer coefficient with distance, and indeed this corresponds again to the growth of the boundary layer, but this decrease in heat transfer coefficient is much more gradual in the case of the turbulent regime. So we can quantify the behavior of the transport processes in the turbulent regime by looking at the mathematical expressions for the friction coefficient and the Nusselt number. Again, we remind ourselves we're looking at this transition from a smooth flow where the stream lines, as we defined them before, that follow always tangent to the velocity of the fluid are smooth and continuous in the laminar regime. And then as we start to approach a critical Reynolds number, we start to see a transition where there is some instability in this flow. And then as we pass through this transition region, we achieve a turbulent flow. And this turbulent flow occurs because the inertia of the fluid is now capable of overcoming the damping that's corresponding to the viscosity, and that allows packets of fluid to move around chaotically. And so we get this chaotic mixing behavior that's the flow is very unsteady, and there's a substantial y velocity or velocity along the y direction that's able to push momentum and thermal energy from the free stream to the surface and vice versa. And so again, for flat plate, the critical Reynolds number where this transition occurs will depend somewhat on the flow condition and the surface condition of the plate, but your book uses a number for Reynolds number with a length scale of x of 5e to the 5th. And that superior mixing results now in a dramatic increase in the ability to bring momentum to the surface and remove thermal energy from the surface. And so this gives us a increase in the friction coefficient. We didn't show a graph of that before, but likewise we'll see an increase in the friction coefficient because we're able to bring momentum from the flow to the surface more effectively. It means the surface is being more effective in slowing down the flow. And we also see a dramatic increase in the Nusselt number. And the Nusselt number also now has a different dependence on Reynolds number. The Prandtl number dependence is still roughly 1/3 or to the 1/3 power, but the Reynolds number is now the Nusselt number has a dependence of Reynolds number raised to the 4/5 power. It's almost linear, and this really is a indication of the increased importance of advection in this mixing region. So if we remember that the heat transfer coefficient is the Nusselt number times the thermal conductivity of the fluid divided by the length scale, in this case just x, and we plug in the expression for the Nusselt number, then we'll see the dependence of heat transfer coefficient on x is now much more gradual. Rather than writing this out, we'll just say h is proportional to 1/x to the 1/5. And so this is what we saw before in the chart. We saw a major jump in the heat transfer coefficient when we moved from the laminar regime to the turbulent regime, and then we saw a much more gradual decrease in the heat transfer coefficient as we progressed in x in the turbulent regime. And it's important to note that it's not really possible to solve the turbulent boundary layer equations under any normal circumstance, or at least a useful circumstance to us. So we're relying on experimental data, experimental correlations for most of the heat transfer correlations relating to the turbulent flow regime. And so for the flat plate, this is the appropriate local, importantly, this is the local heat transfer or the local Nusselt number, and correspondingly the local heat transfer coefficient for a flat plate in parallel turbulent flow. So we considered an expression for the local heat transfer coefficient and the local Nusselt number for turbulent flow. So now we'd be likewise be interested in understanding the average heat transfer coefficient for a plate undergoing turbulent flow. But we need to remember that for a plate seeing a clean free stream, in other words, a well-ordered flow in the free stream, there will always be a laminar region at the front of the plate. So if we're interested in the average heat transfer coefficient for an entire plate, we have to integrate over both the laminar regime that leads up to the transition point. So here we're designating XC, the position of the position that corresponds to the critical Reynolds number. Your book is generally using 5e to the 5th, the critical Reynolds number. So we have this laminar regime that we have to integrate over, and then we also integrate over the remainder of the plate beyond the transition point, which is in the turbulent regime. And if we integrate over those two regimes, integrate the heat transfer coefficient over those regimes, and divide by the total length of the plate, then we get an average heat transfer coefficient. From that, we can define an average Reynolds number, which will have a functional form like this, with a constant times Reynolds number to the 4/5. Again, the Reynolds number here has a length scale of L. We define Nusselt sub L, Reynolds sub L. That means that the length scale here is the total length of the plate. So the Reynolds number would be free stream velocity times L divided by nu, kinematic viscosity. And that's raised to the 4/5 because once we get past the laminar regime, all of the remainder of the plate is in the turbulent regime. The heat transfer coefficient there depends on Reynolds number to the 4/5 minus some constant, which corresponds to the contribution to or is related to the contribution occurring in the laminar regime. And since this integral will be constant for a given Reynolds number, then or constant for a given critical Reynolds number, we can define a constant A that depends only on the critical Reynolds number. Again, your book usually uses critical Reynolds number of 5e to the 5th, so that the value of the constant A here would be about 871. All right, so we've looked at the Nusselt number and heat transfer from a flat plate in parallel flow, experiencing a flow with a free stream velocity defined and a free stream temperature defined. And we've come up with solutions or seen that there are correlations that can describe the heat transfer from this geometry under laminar and turbulent conditions. And we've considered the local and the average values for the heat transfer coefficient. And so we've largely described the possibilities for that geometry, but we've made some specific limitations on that. And most notably, we considered a plate that was uniformly at a uniform temperature over its entire length. So TS was constant over its length, and that included the entire length of the plate. So there are a variety of conditions that we'll often encounter in practice that we also need to consider. And one of the important ones is an unheated starting length. So we might imagine that we have some plate of a given length, and the leading edge of this plate is not heated. So now the two boundary layers develop differently than each other, or at least they start developing at different locations. The velocity boundary layer is developing as soon as the flow hits the leading edge. So the velocity boundary layer is growing, but there is no thermal boundary layer in this leading edge region, or this leading region, because it's unheated and the temperature of the plate will just be at the temperature of the free stream. At a later region of the plate, perhaps we're adding heat to this plate, and now the temperature of the surface of this plate is going to be elevated above the free stream temperature. So now there will be heat flux leaving that surface, and that will result in a growing thermal boundary layer. So in order to consider this case, which is a case that we might commonly run into, we need to define where that heated region begins, and your book defines that length, that unheated length, by the Greek letter xi, and they give you two correlations that you can use, and they're modifications to the isothermal relationship. This is the Nusselt number with the length scale of x for the isothermal plate. Although perhaps I shouldn't even be that limiting. Let's say for fully heated. So we'll designate that as a xi value of 0. So for the fully heated case, this is what we've solved before. We can modify that value to obtain a modified Nusselt number in the unheated case. And for the laminar regime, that modification is given by the fully heated case divided by the quantity 1 minus xi over x to the 3/4 power, that quantity raised to the 1/3 power. And likewise, there's a relationship, a different relationship for the turbulent regime. It looks similar to the laminar regime. Again, this is the fully heated case. And now we are just using different powers in this modification term that relates the unheated length to the position of the local Nusselt number that we're interested in, designated by x. And there's one final case that's of considerable engineering interest, and that's a constant heat flux. So before we were considering a plate with a uniform surface temperature, and now we want to look at the possibility that we have a uniform heat flux and the surface temperature is varying along the length. So heat flux is constant with x, but surface temperature varies along the length. Again, we can arrive at correlations describing these results. So for the local Nusselt number in laminar flow, we see a similar dependence in Reynolds number and Prandtl number to the constant temperature case. Isothermal case, we just see a larger prefactor. So on average, or anywhere, the Nusselt number is larger for the constant heat flux case than it is for the isothermal case. And the same occurs for the turbulent case, although now the prefactor is still larger. We still have the same dependence on Reynolds number to the 4/5, Prandtl number to the 1/3, but the local Nusselt number now is somewhat larger, to a smaller degree than it was for the laminar case, but somewhat larger than the isothermal case. And likewise, we can talk about an average Nusselt number, and now we're not really interested in determining the total heat flux, the total heat rate. The heat rate will just be the heat flux times the surface area that we're interested in. But we may be interested in defining an average surface temperature, which we can define relative to the heat flux and the Nusselt number. So in other words, we could define Newton's law of cooling as the surface heat flux being equal to some average heat transfer coefficient times an average surface temperature minus the free stream temperature. So in order to define this, we need to define an average Nusselt number. And for the laminar regime, we obtain a value, if we integrate, that looks like this. So we get an average Nusselt number over the entire length of the plate as 0.680 times the Reynolds number, again with the length scale now of L, the entire length of the plate. But we notice that this is only slightly greater than the value that we obtained for the the isothermal average. We remember for the isothermal average, we got a value here of 0.664. So this is only about 2% larger. It turns out for the turbulent case, it's even less. This difference is even smaller. So the upshot of this is that it's okay to use the average isothermal results in determining this average surface temperature. We want to make a couple more notes before we finish off with the flat plate in parallel flow. And that's that we want to note that these correlations always have limitations on them. It's important to pay attention to them. One of all of the limitations and all of the conditions. So oftentimes these correlations are limited in terms of what ranges of Prandtl numbers they're valid for. We need to pay attention for where the or at what temperature the fluid properties need to be evaluated at. For all of these correlations we've dealt with so far, that's going to be the average between the surface temperature and free stream temperature. And we also want to be really cognizant that these correlations shouldn't be considered to be particularly exact. They're based on many times the accumulation of a large amount of experimental data, and this describes a good relation of the average of that experimental data, or the most common result from that experimental data. But experiments always have noise in them, and the conditions are always different between different cases. And so these correlations can have rather large variations between the Nusselt number that the correlation gives you and what you may find in experiment. And so a rule of thumb, each correlation should give you some idea of how accurate you should expect it to be, but a rule of thumb is maybe don't consider these to be accurate to much better than maybe plus or minus 25% for any given correlation. Now don't consider that again a precise number, but this gives you some idea of the ranges of errors that you might expect.